Hello everyone, welcome back to another lecture of process modeling and simulation. And the module which we are covering these days is related to the reactors. If we look at the summary, in this reactor, we have to specify the stoichiometry, we have to specify the kinetics. This is a rigorous model and the feed count can be any number. Means you can specify more than one feeds. And this is a rigorous model, and in this example, we will learn some new thing regarding the design spec. If you remember, we have used design spec in distillation column, rigorous distillation column. And here in CSTR, we will be using the design spec and so in plug reactor. But this plug flow reactor, which we will discuss in our next lecture. So this activity is linked with CLO number 1, CLO number 2 and CLO number 4. CLO number 1 is related to the fundamentals, which is linked with the engineering knowledge. CLO number 2 is related to simulation, which is linked with PLO number 5, modern tool usage. And CLO number 4 is the analysis part, which is linked with the problem analysis, PLO number 2. So there are two objectives of the simulation. Number one is to calculate the conversion of ethylene for given reaction kinetics. This is the same reaction which we have studied earlier, that ethylene reacts with benzene to form ethyl benzene. So we will use this kinetic data which we have already used in our batch reactor, which was our previous exercise. And for a given kinetic information and the given temperature pressure conditions, we will see the conversion of ethylene to ethyl benzene. Obviously, benzene is also converting, but the main impact is of ethylene. And using design spec, as I have told you that it's a rigorous model, and we will be using design spec just like we used in the distillation column. But obviously, the procedure will be different. To analyze the volume of reactor for 98% ethylene conversion, that we will ensure that ethylene is converted to 98% Fa0 minus Fa over Fa0, and this conversion should be 98%. First, we will see that what conversion we achieve, and then we will use design spec to take it to 98% and specify tolerance as 0.001. What does that tolerance means? It means the difference between the specified value and the achievable value. कि आपने स्पेसिफाई किया 0.98, अब इस 0.98 को कितना आप टॉलरेट कर सकते हैं, इसमें कितना एरर आप टॉलरेट कर सकते हैं. So that is 0.001. It means 0.98 minus 0.001. It's basically plus minus tolerance. So this is the same window which we have studied in the batch reactor, but let's take an overview of it. Ethylene 298 Kelvin, 15 atm, 50 k mole per hour. Benzene 300 Kelvin, 15 atm, 100 k mole per hour. In reactor specification, we have been given the temperature of 400 Kelvin, the pressure of 10 atm, and here we have been specified the reactor volume, which is 0.1 cum. It is cubic meter, and this is the same kinetic equation, same property package Chauceter. K is equal to k naught exponential of minus Ea over RT. K value is 1.528 multiplied by 10 raised to power 8, and for activation energy it is 7.1129 multiplied by 10 raised to power 7 joule per kilomole. So this is how the components are added. Chauceter is specified. CSTR, as you can see, there are two feeds to it. Then the reaction set. This is the stoichiometry, which is given based on the equations and rate of reaction equation. Then this is specified. Then benzene, ethylene are specified. Then this is the new interface for you. Obviously, this is for CSTR, where you have specified pressure and temperature. Again, if you see, these four are the same specifications which we have used in flash separator. So pressure 10 atm, temperature 400 Kelvin, valid phase, obviously it's a liquid phase reaction, so we will select liquid only. The volume of the reactor is 0.1 cubic meter. Reaction is specified, it's run. And then here at this point we will calculate the percentage conversion. Then we will go to this flow sheeting option, and in design spec we will click on new, okay. And it is the same procedure as that of the sensitivity analysis in our previous activity, that here define it is first. उस केस में क्या था कि सबसे पहले आप वेरी को डिफाइन करते थे. In that case you have to define, or you have to give the value of vary first, then define, then tabulate. Here you have to define the dependent variable first, which is your obviously the value of ethylene. You know that you have to specify ethylene in and ethylene in out. It is same if you recall the previous lecture of batch reactor, that both these are same because there we have specified ethylene in minus ethylene out over ethylene in. That was a formula of conversion. But for this initially we had to specify the two parameters, जो कि दो पैरामीटर आपको बताने पड़ेंगे यहाँ पे, कि एक तो इथाइलिन इन है जो कि ई इन है, और इसी तरह इथाइलिन आउट. When you have specified ethylene and ethylene out, then you have to go to spec, which is similar to the tablet, and you have to first provide the spec. If you have been asked to just only estimate or know the value of a certain number, then you have to just give the value. मतलब अगर आपको ये कहा जाता है कि इथाइलिन आउट जो है वो फॉर एग्जांपल 200 kg मोल पर आवर, तो आप क्या करते हैं, यहाँ पे इथाइलिन आउट लिखते, यहाँ पे टारगेट में 200 लिखते, और यहाँ पे आप टॉलरेंस लिखते. लेकिन अब इस केस में क्या है कि आपको कन्वर्जन चाहिए, आप चाहते हैं कि परसेंटेज कन्वर्जन इथाइलिन की कितनी हो, 98%. तो आप क्या करेंगे, फॉर्मूला लिखेंगे x इज इक्वल टू एफ ए नॉट विच इज ई इन माइनस एफ ए ई आउट ओवर एफ ए नॉट ई इन, with target as 0.98 and tolerance at 0.001. Then you go to vary, block variable, CSTR, its volume. You have to vary the volume as it was mentioned. This is the lower bound, this is the upper bound, this is the step size. After that, you get your result. I will stop it here and I will move to the simulation before going to the next slide, because we will come at this slide after doing this stuff. So first we will add the component. Ethylene is added, benzene is added, and ethyl benzene, you can write EB, ethyl benzene is automatically added. In previous case we had mentioned ethyl benzene here. Then click on next, select chow cedar, and then after running go to the simulation environment. Here in reactors, this is the CSTR reactor, so you will click it, place it over here, and then we'll do the connections. If you see feed required one or more, so first feed will be benzene and the second feed will be ethylene, so I will label it as benzene B and ethylene E. Even this can be ethylene and this can be benzene, there is no issue. The issue was there in the previous exercise, and this is ethyl benzene EB. And after that specify both ethylene and benzene, and I will just skip it step in the video and I will show you the final values. So as you can see, benzene is specified 300 Kelvin, 15 atm, 100 k mole per hour, and mole fraction of benzene is 1. Similarly, ethylene is specified, and you can see 298 Kelvin, 15 atm, 50 k mole per hour, and ethylene mole fraction is 1. Now we will go to the CSTR reactor, and in this reactor the pressure is 10 atm, the temperature is 400 Kelvin, the valid phases is liquid phase reaction, so we have to specify liquid. If by mistake you do not specify it as liquid phase, there will be an error in the system. You can check it as well. This is total reactor volume and the current unit is liter. So it's CUM, cubic meter. If it's cubic feet, that's CUFT, and the given value is 0.1 cubic meter. So once after giving this information, this tick button has been active. So it means you have to specify at least 4 values: pressure, temperature, valid phase, and either reactor volume or residence time. In this case, we have to specify the reactor volume. Then go to the reactions and click on this new, and we have already done this step in our previous exercise. Go to this power law, click OK, then click on new and specify ethylene benzene reacts to form ethyl benzene, -1, exponent 1, 1, and coefficient 1. I am not repeating it because we have already discussed it in batch reactor in detail. Then go to the kinetics. The reacting phase is liquid, should be same as that of the reactor. And in the next exercise, which is related to the plug flow reactor, we will see it in detail. 1.5 to 8 multiplied by 10 raised to power 8. Convert its unit to joule per k mole. 7.1129 E of 7. And after that, simply run it. And you see results are available. Go to main flow sheet, right click, go to the stream results, and see what is the percentage conversion of ethylene. For this, go to mole flows. Ethylene at inlet is 50. At outlet, it is 4.45344. So if I calculate it, is 50 minus 4.45344 divided by 50 multiplied by 100. So it is 91% or 91.1% conversion of ethylene, which have been achieved by giving the values as given to us, that we have specified 10 atm pressure, 400 Kelvin, and with reactor volume of 0.1. Obviously, if we want to increase the conversion, we have to increase the volume of the reactor. This is obvious. But what should be the value? Obviously, we can't do hit and trial, because what is the purpose of simulation then? There is no mean of doing simulation if you have to do the hit and trial. So for this purpose, we need to go to the much cleverer way, much efficient way. And this efficient way is to go to the design spec. What we do, flow sheeting options. This is the design spec. Click on this new. Okay. Similar to the sensitivity analysis, but in sensitivity analysis, we analyze it, but there is no impact on the back, that no condition of CSTR will change. But with this design spec, the condition will change. How? I will show you. So what you do, this is define. If you remember the define of sensitivity analysis, click on this new and first define it as E in. Give the variable name. What is it? Mole flow. Of what stream? Inlet stream, which is E. Of which component? Ethylene. If you make any mistake in choosing it, your answers will be wrong. Then click on this new E out. Then mole flow of EB, which is the ethyl benzene outlet. Of which component? Ethylene. So you have specified two components, that ethylene, which is ethylene in the feed stream, which is E, and ethyl out, which is ethylene in the outlet stream EB. Then go to the spec and specify the formula. E in minus E out over E in. And the target value is 0.98. And if I take you to the tolerance, absolute tolerance between spec and target expressions, constant or Fortran expressions. But obviously we will specify it 0.001. Then go to this vary, similar, but interface is a bit different. Block variable B1, and in variable we have to vary the volume of the CSTR. What you do, we go here. This is the specified reactor volume. This is the estimate for the reactor volume. You do not have to select estimate. You have to select specified reactor volume. And the unit should be in cubic meter with 0.1 to 2 with a step size of 0.1. It's necessary to give step size, although even without giving step size, it will also convert, but it's better to make different steps to get accurate results. Then run it and you see results are available. So how you can view these results? Go to this DS1, you have specified the input, which was this, and go to this results. And you see that E in is 50, E out is 0.976. So if you 50 minus 0.976424 divided by 50 multiplied by 100. So you see 98.05% conversion is achieved. A bit higher than you required. Obviously it's 98%. We all agree कि ये 98% ही अचीव हो गया, लेकिन ये थोड़ी सी ज्यादा है वैल्यू. यहां से मैं आपको अगली स्लाइड पे लेकर जाऊंगा, जो कि आपकी 10th नंबर स्लाइड थी, या जिसका पॉइंट नंबर 10 था. That for this conversion it's also fine, but if we strictly follow 98%, then what we have to do? We have to vary this tolerance over here, because if we increase this tolerance, means if it is 0.0001, then this value will come closer. If it's 0.tetra01, then this value will almost match. So question number 1 is that are you able to achieve required conversion? Yes, but a bit higher. So it means that the conversion still needs some improvement, because it is 98.05. Obviously you can say, oh, it's 98%, doesn't matter, but definitely not. You need to achieve exact 98%. So how will you achieve it? The hint is the tolerance. So what you do, you come back to this point, vary it to 0.0001, reset it and run it, and go back to these results to see whether you have achieved it or not. It is 50 minus 1.00086 divided by 50 multiplied by 100. 97.998. Yes, this is acceptable value. Or if you want to increase it further, again go to input and go to this point tetra01. Again reset it, again run it. Make sure to reset it to avoid simulation crashes. And you see 50 minus 1. Exact 50 minus 1 divided by 50 multiplied by 100. Exact 98% conversion. Best result of this. So you have to vary the tolerance in this case. If it's a specified value, you cannot vary it. But obviously in this case, I have also added a possibility that if you are not specified tolerance, or if you specify tolerance, in order to achieve the required value, कि आपने required value achieve करनी है, ठीक है, आप tolerance को vary करें. अगर तो आपको पेपर में कह दिया गया कि ये टॉलरेंस यूज करनी है, फिर तो आपने वही टॉलरेंस यूज करनी है, चाहे उस पर फिर जो मर्जी आंसर आ रहा है. लेकिन अगर आपको पेपर में नहीं कहा गया टॉलरेंस का, तो फिर आपने अपनी मर्जी से टॉलरेंस को इतना वेरी करना है, लेकिन बहुत ज्यादा वेरी भी नहीं कर देना. ठीक है, ये इसकी एक लिमिट्स होती हैं, जो कि आप इंटरनेट से भी देख सकते हैं, और उसके करस्पॉन्डिंगली आप लोगों ने वैल्यूज को अचीव करना है. एंड यू सी दिस इज द परफेक्ट रिजल्ट एट दिस टॉलरेंस लिमिट, which is 0.tetra01. This is a very small, because we want exact answer from the Aspen. That's how you simulate the CSTR reactor in Aspen Plus. In our next exercise, we will go with the plug flow reactor, the last exercise of this reactor module. After that, that is a reactor comparison. But obviously, it will be combining all these reactors which we have studied. It's thank you so much.